In the late 1930s, an ambitious dream was taking shape over Washington's Puget Sound, a bridge to connect two communities. Engineers envisioned a structure of unprecedented grace and slenderness, a testament to modern design principles and materials. Construction began with immense effort as workers toiled to erect the colossal towers that would support this modern marvel. Massive anchorages were sunk deep into the earth, designed to hold the immense tension of the suspension cables. Day by day, the bridge stretched further across the Narrows, a thin ribbon of steel against the vast landscape. The design was revolutionary, featuring a solid, shallow plate girder deck instead of the deeper, open trusses of older bridges. This choice, made for aesthetics and cost, would later prove to have unforeseen and dramatic consequences for the structure. As the final sections were put into place, a sense of accomplishment filled the air. The project was nearing completion. The Tacoma Narrows Bridge stood as the third longest suspension bridge in the world, a symbol of human ingenuity. But from the very beginning, this elegant giant held a secret, a hidden tendency to move in the wind. On July 1st, 1940, the Tacoma Narrows Bridge opened to traffic, hailed as a masterpiece of modern engineering. Its slender profile and incredible length were unlike anything the public had ever seen before. It was breathtakingly elegant. Drivers marveled at the smooth ride and the stunning views afforded from the center of the massive span. It was more than a bridge. It was a destination, a symbol of progress that connected previously distant shores. The local community celebrated its completion, foreseeing a future of growth and prosperity thanks to this new connection. Newspapers and magazines featured stunning photographs, praising its graceful lines and the daring vision of its creators. The lead engineer, Leon Moissafe, was a celebrated designer, and this was considered another of his great triumphs. His theories on deflection allowed for lighter, more flexible, and more economical suspension bridge designs than ever before. For a few short months, the bridge fulfilled its promise, effortlessly carrying thousands of vehicles across the Narrows. But this idyllic period was fleeting, as the bridge's unique character would soon begin to reveal itself in alarming ways. Almost immediately after opening, reports began to surface. The bridge wasn't entirely stationary. It had a strange bounce. Even on moderately windy days, the long, thin road deck would begin to rise and fall in gentle, rhythmic waves. Construction workers had noticed it first, feeling the deck undulate beneath their feet long before it opened to cars. At first, it was a curiosity, a peculiar characteristic of this uniquely flexible structure, not a cause for alarm. The movements were often several feet high, yet they were slow and graceful, like a giant steel creature breathing. Engineers were aware of the motion, but believed it was within the bridge's designed range of flexibility and posed no danger. They installed hydraulic buffers and anchoring cables in an attempt to dampen the oscillations, but these had little effect. The public, however, was growing more aware. Driving across the bridge became a memorable and sometimes unnerving experience. The car in front of you might disappear into a trough, only to reappear moments later as it crested a wave. This strange behavior earned the bridge an affectionate but prophetic nickname, Galloping Gertie. The name would stick. The legend of Galloping Gertie spread quickly. The bridge became less of a utility and more of an amusement park ride. Thrill seekers would drive to Tacoma specifically to experience the sensation of the bridge's gallop on a windy day. They would feel their cars lift and fall, a sensation somewhere between a gentle swell and a roller coaster drop. Some found it exhilarating, a unique quirk of their local landmark. Others found it deeply unsettling and avoided it entirely. The motion was so pronounced that university professors brought their physics students to witness the phenomenon firsthand. They studied the waves, measuring their amplitude and frequency, trying to understand the forces at play on the structure. Despite its fame, the constant movement was a sign of a fundamental instability in the bridge's aerodynamic profile. The solid girders on its sides acted like an airplane wing, catching the wind and generating lift, causing the deck to rise. For 4 months, this strange dance continued. The bridge galloped, the people watched, and the wind kept blowing. But the performance was building towards a finale that no one could have truly anticipated. A day of reckoning was near. The morning of November 7th, 1940, dawned gray and stormy. A wind of about 40 miles per hour swept through the Narrows. This was not unusual for the region, but on this day, the wind's effect on the bridge would be different. At first, the bridge began its familiar gallop, with waves of 3 to 5 feet, a common sight for locals. But around 10 a.m., the character of the motion changed dramatically. The galloping stopped, replaced by something far more sinister. A twisting motion began. The bridge started to rotate around its center line, one side rising as the other fell. This was a torsional or twisting flutter. the very phenomenon that engineers had believed their design would resist. The wind speed, by a quirk of fate, had reached the exact velocity needed to induce this catastrophic resonance. The bridge had found its harmonic frequency, and the wind was now pumping energy into it like a person pushing a swing. Authorities quickly closed the bridge to traffic, realizing the situation was escalating beyond anything seen before. On the twisting span, only one car remained, its driver having abandoned it moments before. The bridge was now alone with the wind. The twisting motion grew more and more violent. The bridge was no longer galloping. It was engaged in a chaotic, terrifying dance. The deck tilted at angles of up to 45 degrees, first one way, then the other, in a sickening rhythm. Lampposts on the side of the bridge were sheared off by the extreme flexing of the steel. The main suspension cables, normally taut, were seen slackening and then snapping tight with each twist of the deck. The phenomenon is called aeroelastic flutter, where aerodynamic forces couple with a structure's natural vibration modes. The energy being fed into the bridge by the wind was now far greater than its ability to dissipate it. From the shore, horrified onlookers, including the bridge's own engineers, could only watch, powerless to intervene. The sound was described as a deafening groan, a symphony of tortured metal echoing across the water. Each oscillation pushed the materials further past their limits, stretching and compressing the steel beyond its breaking point. The bridge's elegant dance had become a final, desperate struggle against the relentless power of the wind. In the midst of this chaos was a single car, a coupe belonging to local newsman Leonard Coatsworth. He had been forced to abandon it when the motion became too violent to drive, crawling to safety on his hands and knees. But he had not been alone in the car. In the back seat was his daughter's cocker spaniel, Tubby. Paralyzed by fear, the dog refused to leave the vehicle, even as Coatsworth tried desperately to coax him out. As Coatsworth made his perilous escape, he looked back at the car, a lone, dark shape on the wildly moving bridge. Later, another man, a university professor, bravely attempted to walk out onto the bridge to rescue the dog. He reached the car, but the terrified dog reportedly snapped at him, refusing all attempts at rescue. Defeated, he had no choice but to retreat, leaving the car and its sole occupant to their fate. This small, personal story added a layer of tragedy to the immense structural drama unfolding before the world's eyes. The car and the dog became a focal point of the disaster, a symbol of the life caught in the path of unstoppable forces. At 11 a.m., after an hour of violent twisting, the inevitable happened. The first piece of the structure gave way. With a sound like a cannon shot, one of the main suspension cables snapped near the center of the bridge. The loss of support from the cable caused a section of the road deck to sag and then break away completely. A huge plume of water and concrete dust erupted from the Narrows as the massive section made impact below. This triggered a chain reaction. The unbalanced forces on the remaining structure became insurmountable for the materials. More cables began to fail, their connections to the deck ripping apart under the strain of the erratic motion. Piece by piece, the rest of the center span tore itself apart, plunging into the churning water of the Puget Sound. The side spans, suddenly relieved of the central span's weight, sagged dramatically, dropping more than 60 feet. The great towers, though damaged, remained standing, stark sentinels over a scene of total structural ruin. In just over an hour, the third longest suspension bridge in the world had completely destroyed itself. In the aftermath, a stunned silence fell over the Narrows, broken only by the wind and the groaning of twisted metal. Where a graceful ribbon of steel had once stood, now there was only a jagged, gaping void. The main cables, once pulled into a perfect parabola, now hung uselessly from the towers like giant frayed ropes. Shorter vertical suspender cables dangled from the main lines, swaying in the wind like a bizarre metallic fringe. Engineers and officials, including a devastated Leon Moiseev, arrived to survey the unbelievable scene of destruction. The side spans, though still standing, were warped and buckled, their structural integrity completely compromised. The wreckage in the water below was a tangled mess of steel girders, concrete, and rebar, a tombstone for the fallen giant. The financial loss was immense, but the blow to the engineering community's confidence was even greater. How could a structure designed with the most modern principles have failed so spectacularly and so publicly? The failure of Galloping Gertie was not just a local disaster, it was a global engineering crisis that demanded answers. The investigation into the structural failure began almost immediately, led by a board of top aeronautical and structural engineers. The key to understanding the failure lay not in the strength of the materials, but in the bridge's response to wind. Engineers built precise scale models of the bridge and tested them in wind tunnels, a practice previously uncommon for bridges. In the controlled environment of the tunnel, they were able to replicate the exact torsional flutter that destroyed the bridge. The solid plate girders were the culprit. They created large, unstable vortices of air that pushed the bridge into oscillation. The solution was to return to deeper, stiffer truss designs that allowed wind to pass through the structure harmlessly. A new, much more robust Tacoma Narrows Bridge was built in 1950, incorporating all the lessons learned from the failure. Today, aerodynamic stability and wind tunnel testing are fundamental, mandatory parts of any major bridge design process. The dramatic end of Galloping Gertie was a costly but invaluable lesson for the entire field of engineering. It taught us that even the most impressive structures must respect the subtle but immense power of the natural world.